Okay, hello. Thank you everyone for joining us. Good morning, good afternoon, depending on which time zone you're in. My name is Monica Harvey, and I am a policy analyst in the Climate Change Impacts and Adaptation Division at Natural Resources Canada. On behalf of the Flood Mapping Committee, I wanted to thank you for joining us on Friday for a webinar on the case studies on climate change and flood mapping. Thank you also to the CWRA for hosting as well. We have a lot of people registered, over 200, so that's great. And just to let you know, we put you all on mute if you've called in. Okay, so the case studies on climate change and floodplain mapping was released last month and is part of the federal guidelines for floodplain mapping, a series of guidelines documents that provide guidance to support flood mapping activities in Canada. The guidelines are developed under the leadership of the Flood Mapping Committee, which is a partnership between Natural Resources Canada, Public Safety Canada, Environment and Climate Change Canada, Infrastructure Canada, Crown Indigenous Relations and Northern Affairs Canada, the National Research Council of Canada, the Department of National Defence, and the Defence Research and Development Canada. So it's an interdepartmental committee. So we're here to learn more about climate change and flooding and floodplain mapping. As you may know, the latest IPCC report states that the global average temperature will reach an increase of 1.5 degrees Celsius between 2030 and 2052, if we go at the current rate that we are. And under these conditions, we are likely to see changes in heavy precipitation in several regions. As we know, that warming not only affects precipitation, but also alters other aspects of the water cycle, increasing evaporation, changing precipitation patterns and intensity. It affects processes involved in the storage of water, things like snowpack, snow melts, river ice breakup, and glacial melt. And many of these processes are active in flood generation. These changes can cause floods not only to increase, but also decrease as well, and are very regionally and watershed dependent. Despite the potential for a decrease in floods in certain areas, it is estimated that in the next 20 years, the total global economic losses due to floods will increase by 17% globally. So with these potential effects of climate change on flood risks, there is an increasing need to understand and plan for these potential changes. And one way is through the incorporation of climate change into flood mapping. So traditionally, flood mapping uses historical data, and so the use of climate projections in flood maps is a new and emerging field with no sort of best practices or sort of common accepted methodologies. So this is why for this document, we've taken a case studies approach where we essentially provide examples of methods that early adopters have used that can be considered by other people in their flood mapping activities. So we have 3 case studies, 2 in BC and 1 from Newfoundland, and we are fortunate enough to have the case study authors here to present their work to you. So we'll go through the presentations and then have some time at the end for questions. As we go, you can type questions in the chat box and we'll answer them after all the presentations. So the first presentation is the case study on the City of Surrey, and we have 2 presenters. The first presenter will be Carrie Barron. Carrie Barron is a professional engineer with over 30 years of experience in municipal water resources and environmental engineering. She is the drainage manager for the City of Surrey, whose responsibilities include overseeing the function of the natural and man-made drainage systems, floodplain and dike management, climate change adaptation, and sea level rise planning activities. The next presenter on the City of Surrey case study is Monica Manistrom, and she is a principal of Northwest Hydraulic Consultants and has over 30 years of experience in hydraulics, hydrology, and sedimentation engineering. Her background includes assessment of flood hazards and risks, floodplain mapping, and management studies. So if you give me a moment here to pull up the presentation, I will let Carrie start.
There we go. Good morning, everybody. So I'll give a bit of an introduction into Surrey and a bit of the topography, etc. And then Monica will go into the details of what the study was and everything we've done. Next slide. So again, in this intro, there'll be a video, just a short video that we made to describe our coastal flood adaptation strategy that we're working on. The video was done approximately 2 years ago. We're at the end of our study right now, so just it sounds like we're not, but we are. And then talk about Surrey today. So let's go into the video. I think we don't have sound in the video. Or I can talk about what the video is showing you at the same time. So really what we were doing is talking about the floodplain extents of our coastal area and the different kind of geographical features that are there. How do you want to do this, Monica? Let's keep playing it, and then hopefully it shows up on, people can go back, because I wasn't too sure how you're getting your volume or not.
Okay. Sarah, are you there? Okay.
So this, again, this is just one of our counselors who was talking about how the need to address climate change now for future generations and our CFAS project. This shows you a bit of kind of what they think the tides, this is tides we're seeing right now, which are only going to get higher by a meter is what the province is predicting. This is kind of our coastal floodplain area of Surrey, which includes Semiahmoo First Nations, residential, agricultural areas, transportation, huge diking infrastructure, and significant environmental areas. We have about 100 kilometers of dikes along this, which protect the city from flooding. These are shots of flooding we actually have from time to time. Earlier this week, we had some more. And the extent of the dikes, which are only built for today conditions, not for 1 meter of sea level rise. And so it's just the amount that will cost is projected to be over about $1.5 billion to improve dikes for sea level rise in the community. And that was 2013 dollars. So we started this adaptation process where we're engaging stakeholders, we're talking to people, we're trying to build the awareness and explore what we should be doing, because it's not necessarily just about building dikes higher. And going through all kinds of stakeholders, public, utility organizations, the farmers, hosting tours, showing people what it looks like, showing what it may look like in the future, having people who've lived in the area talk about what they've seen over time, just to develop a strategy of moving forward into climate change. And so you're just seeing pictures of the various different open houses, workshops, etc., with interest groups. 5 areas: community residential, environment and recreation. For these are transportation infrastructure, agriculture and farming, and then also are the huge big industry ones. The next phase, which has already been completed, is what we can do. So we're exploring our options of how do we preserve, how do we manage for the sea level rise. And manage doesn't mean that we're necessarily going to keep all the land as it is in the current form. How are we going to address this in the future? So this is a project we have going on now, and there's a coastal@surrey.ca is where you can see this video and other videos and a lot of our information, including to where we are. We're in phase 4 right now, about to put forward a draft report to council. Yeah, go to the next one. So give you a context of where Surrey is for those who don't know. We're in the Metro Vancouver area. We have almost 600,000 people now, one of the fastest growing in BC. Quite a large area, 54 kilometers of shoreline between Boundary Bay and Fraser River. A lot of dikes, a lot of fisheries creeks. Council in the early days adopted the not to enclose our creeks, but leave them open. Next slide. We have different stormwater planning areas. So we have the blue areas are the various floodplains, true floodplain areas that we have in Surrey. Then we have like upland areas. We have floodplains that are not protected by dikes. We have floodplains that are flood controlled, not flood protected. And we have like upland areas, and we have some historic settlement areas. We're going to be concentrating mainly on our coastal agricultural areas, kind of in the middle blue section there that you can see. Next slide. We have been doing a lot of studies on climate change and stormwater, not just for our lowlands coastal areas, but throughout Surrey. From some of our trending studies, you can see here, depending on what happens, we could go up anywhere from 68 to 154% for rainfall, depending statistically what happens in the future with climate change. But and this is just giving us some time frames. It doesn't mean it's going to stop when we hit 2080, but we are going to have some significant changes. And what does that mean to our community? Next slide. So Surrey has been planning. We've done 2 sustainability charters now. We have 2.0 was our updated one. We have a climate adaptation strategy, a community climate action strategy. We've been updating a lot of our plans to how do we deal with climate change. Next slide. And it's not just on rainfall. We're looking at what does it do to our natural environments, heat islands, energy, agriculture, sensitive ecosystems. We're trying to look at the climate change as a whole process, not just one aspect such as sea level rise or one aspect of precipitation change. Next slide. And also trying to adapt now for end-of-life conditions. So when somebody's rebuilding a house in a floodplain, you don't rebuild it to the lower level. You rebuild it to what's going to be end-of-life conditions in, say, 100 years. When we're rebuilding pump stations, that's the middle one. That pump station was designed for end-of-life in 100 years. Pumps can be changed out, shafts can be extended, electrical panels have ability to move within the housing, and then also let's not put people in dangerous areas. So we've done hazard lands development permit areas now, so that if you are designing on a steep slope or in a floodplain, you have to design differently. Next slide. And then it's Monica now.
Thanks, Gary. Can everybody hear me? I hope so. Hello, bonjour. My name is Monica Mannerström. Quite a bit of technical work has gone into understanding the flood hazards in Surrey. It's such a complicated system. There's the Serpentine River, the Nicomeco River, sea dams, many pump stations, flood boxes, culverts, spillways, storage cells, and so on. So in the next 10 minutes, I'm going to summarize about 8 years of engineering assessments. So I think maybe hold on to your hats. Next slide. So there are two types of flood hazards, coastal and riverine. The coastal flood hazards are typically caused by high tides in combination with storm surge, wind, and wave setup. And river hazards are from heavy precipitation, rain and snow events, and typically in combination with long duration high tides that prevent the floodwaters from draining from the lowlands. Next. So how do you figure out the joint probability of coastal and river flooding? We use the continuous simulation approach, since we know that to reliably estimate the 200-year flood, you need about 50 years of records. We had to come up with 50 years of ocean levels, then 50 years of precipitation records, and by inputting these into an HSPF model, we could come up with 50 years of flow records in turn. And these were used in a HECRAS model to estimate 50 years of water level records throughout the basins. And then we could plot these annual peak water levels at each location of interest and extract the 200-year water level at all these different points. Next. So with climate change, we know there's going to be sea level rise. Our provincial government suggests that we use an estimate of 1 meter over this century, understanding that this may change and may need to be updated in the future. Next. Hello. Next, please. Right. And flood flows will increase as well. With increasing temperatures, the air will hold more moisture, and this will result in increased rainfall. Also, with additional development within Surrey, the ground absorption rates will be reduced. Next. So developing future precipitation time series, that's really not all that straightforward. From PCIC, our Pacific Climate Impact Consortium, they downloaded precipitation projections for 12 global climate models. Greenhouse gas emissions were assumed to correspond to the RCP 8.5. That's the highest representative concentration pathway. Our in-house climate scientists looked at a moderately high and an extreme scenario, and based on those developed future precipitation time series based on the historical values that represent the end of the century. Next. So once we have had the adjusted ocean levels for sea level rise, and then also the adjusted precipitation records, we could generate future flow records, plug those into the HECRAS model, and then develop new flood or water level frequency curves for basically end of the century. Next. So this slide compares a frequency curve developed for 2010 and then another curve for 2100. So we can on the y-axis is water level, on the x-axis the chance of exceedance, and on the top return period in years. So we can also see that what this 200-year event today is actually going to have a return period of less than 2 years at the end of the century. So this is clearly of great importance to city of Surrey, which is right on the coast and has a very low-lying floodplain. Next. So based on this output from the frequency curves, we could then plot the flood profiles throughout the Serpentine River and same on the Nicomeco River. Next. And by the same token, we could plot the flood extents across the floodplain. This is at different time steps into the future. The dark purple is for basically today, and then we step forward in increments of 2040, 2070, 2100, and the light pink is what we expect to be inundated by year 2200. Next. So clearly there's a lot of uncertainty with these estimates, but it's something to go by. We don't know how future emissions will look, what the greenhouse gases will be. There's a lot of uncertainty in the global climate system response, and there may be regional variations that are very difficult to project. Next. Next, please. So in summary, these are plausible representations of the future, but they really don't provide specific predictions. Surrey is wise in preparing for future conditions, and this CFAS project that unfortunately you didn't hear the video sound at the beginning, but it's clearly going to be very important moving forward. And thank you. That's all for me.
Okay, thank you very much, Carrie and Monica. That was great. Apologies for the sound not working on the video, but I thought Carrie did a great job of speaking over it. We will send a link to the video along with the slides and a recording of the video this weekend. So thanks again. So next up we have Steve Litke from the Fraser Basin Council, who will be talking about the case study in the BC Lower Mainland for Fraser River and Coast. So Steve is a senior management responsible for the Fraser Basin Council's Watersheds and Water Resources Program. Steve and the Council are currently facilitating the development of the Lower Mainland Flood Management Strategy, which includes flood mapping and climate change as key components. So yeah, thanks. Go ahead, Steve.
All right. Well, thanks very much. I really appreciate the opportunity to participate in the webinar, and I do want to thank Natural Resources Canada for the opportunity to develop the case study. So yeah, this case study focuses on the Lower Mainland of British Columbia. This is a air photo of where the Pitt River joins the Fraser, just to provide a little bit of a glimpse of the region. Next slide, please. And this map here shows the Fraser River Basin and where it's situated in the province of BC. The Fraser River drains about a quarter of the landmass of BC, so a very large watershed that enters the ocean at Vancouver and Richmond, where the red star is on the map. So a very large area, very diverse biophysically, as well as socioeconomically, and very complex hydrology, and quite a wide range of climates and different elevations, mountainous regions, lowlands, etc. Next slide, please. Now we're going to zoom into the Lower Mainland, which is in the bottom left of that BC map. If you go back one, yeah, thanks. So this is the Lower Mainland, and this is the area of the study for this case study. So the mouth of the Fraser enters the Salish Sea at Richmond and Vancouver. And this case study extends about 165 kilometers upstream to the District of Hope, and also extends north along the coast to the District of Squamish. And the flood strategy and this case study look at both Fraser River freshet flooding, which occurs in the spring as a result of snowmelt, as well as coastal storm surge flooding, which occurs more typically in the winter when storm surges coincide with high tides. Next slide, please. So this initiative is not looking at those intense localized rain events as were mentioned in the Surrey case study. There's a number of factors that led up to the flood strategy and the vulnerability assessment. Most notably was the cost of adaptation report, which was commissioned by the province of BC and released in 2012. And that report looked at some cost estimates for the incremental costs of addressing or improving flood protection, flood hazard management to address 1 meter of sea level rise. And the price tag was about $9.5 billion, which was kind of jaw-dropping and certainly got a lot of attention. And a number of the partner organizations we've been working with on flood management expressed an interest in doing some proactive planning on a regional scale and taking a collaborative approach. And so that was the impetus for the Lower Mainland Flood Management Strategy. And then one of the projects was the basis for this case study. Next slide, please. And we implemented the strategy through a phased approach. And in phase one, we are really focusing on improving our understanding, our knowledge base about the nature of the flood hazards, the nature and extent of flood vulnerabilities, what kinds of assets and infrastructure and populations would be at risk. And we also took a look at the status of existing flood protection, diking systems, land use policies, those sorts of things. And we're very interested in not only looking at the present day flood hazard, but the influence of climate change on both riverine and coastal flooding generally, but also within this regional scale vulnerability assessment. And the infographic on the right just shows some of the steps that were undertaken to integrate climate change. So very much as what Monica had described, starting with looking at greenhouse gas emission scenarios, then looking at the projected climate change impacts associated with those scenarios, changes in temperature, precipitation, ocean levels, and river hydrology. And then based on those effects, calculate water levels associated with different flood scenarios for both Fraser River and coastal flooding. And then the fourth step was then to map the extent and depth of those flood scenarios. Next slide, please. So these graphs show a couple of different things. On the upper left show projected increases in river flow. And on the right, the top, you've seen this on the previous presentation, projections for sea level rise. And in BC, we're looking at, for now, considering a 0.5 meter by 2050, 1 meter by 2100. And then because our study area wants to look at both riverine and coastal flooding, we overlay those projections and take the highest water level generated. So the bottom graph of flood profiles on the left is the mouth of the Fraser, and where storm surge is the dominant flood event. And then as you move to the right, you go sort of upriver, and the riverine flood profile is dominant. But basically looking at increases in both coastal and riverine flooding. This table shows the 4 scenarios that we are looking at for the vulnerability assessment. These were recommended by a firm, Kerwood Lydell, with oversight by an advisory committee. And so these 4 scenarios were recommended. A present day coastal flood, that's scenario A, so present ocean levels, but adding a 1 in 500 year storm surge event, or 0.2% annual exceedance probability. And so 3.4 meters relative to the geodetic datum is the water level. And I should acknowledge, because this was for a regional scale vulnerability assessment and because of budget limitations, we didn't look into the localized wind and wave effects and ground subsidence or uplift. We were just looking for a common water level from a large coastal flood as a basis for assessing vulnerability across the region. The second scenario, scenario B, is simply adding a meter of sea level to that. So 4.4 meters geodetic, projected out to the year 2100. Scenario C is the Fraser freshet flood scenario based on the current design event, and that is a recurrence of the 1894 Fraser River flood. And that had a peak flow of about 17, or estimated to be 17,000 cubic meters per second at Hope. And that's been estimated to be close to 1 in 500 year return period as well. And then scenario D is the other climate change projection, also going out to year 2100, taking into account the effects of moderate climate change. And the science of that time suggested an equivalent flood to that 1894 flood would have a higher peak flow, approaching 20,000 cubic meters per second at Hope. And then we did also factor in a meter of sea level rise for this scenario, which definitely affects water levels at the lower end of the Fraser. Next slide, please. I probably don't need to go through this. This is very similar to what Monica had presented, just and everyone on the webinar would be aware of many sources of uncertainty when we're looking at climate change, and particularly looking at climate change influence on flood scenarios. So I don't think I'll read those, but just move on to the next slide, please. So we have those 4 scenarios and then proceeded with mapping. And so on the coastal scenarios, we basically took those water levels, 3.4 meters and 4.4 meters geodetic, and extended those water levels across the landscape until it meets high ground. And so those are the flood extents that you would see closer to the ocean on the left of the slide. The light blue indicates the additional extent of flooding in that year 2100 scenario, and the dark blue is the present day storm surge. Now, I should acknowledge these assume that there are no dikes in place or that they would all be overtopped, and it does not account for the flood duration that might be associated with a specific storm surge or the tide cycle. So a simplistic approach for sure. On the riverine flood scenarios, we looked at the water levels that would be generated by those peak flows if they were confined to the river corridor between the dikes. And then we extended that water level across the landscape again until it hits high ground. So then we proceeded with vulnerability mapping. So we had the flood extents. Again, the dark blue shows the present day design flood. The light blue around the edge is that additional extent of flooding with the higher peak flow in the year 2100. But we wanted to see what assets, what infrastructure, what communities are within these flood inundation areas. This is a zoom in to a portion of the city of Chilliwack. The green line work indicates a number of First Nations reserve lands and communities. In this region, there's about 30 local government entities and about 30 First Nations communities as well. So very significant flood risk in terms of the community impacts. Some of the other critical facilities have to do with emergency services, fire, ambulance, police, hydroelectric substations, schools, those sorts of things. We've got a better sense now of what critical assets, facilities, infrastructure are vulnerable to flooding. Next slide, please. We also did, in addition to extent, we looked at flood depth mapping for the 4 scenarios, and this is more in the Metro Vancouver area, Burnaby, New Westminster, Surrey, Delta. And probably hard to see on this map, and this is the year 2100 coastal scenario, so with a meter of sea level rise. And the flood depths at the yellow end are from 0 to 0.5 meters, and then the darker blue is over 5 meters of flood depth. And I should say that this work was not intended to generate official floodplain designation maps. It's more intended to learn about the hazards, learn about the influence of climate change, and to inform longer-term flood mitigation planning. Next slide, please. We have been working with First Nations and consulting with First Nations on the flood strategy overall, and we definitely wanted the interests and perspectives and assets of First Nations communities to be part of the mapping project and part of the larger flood strategy. So we've done some initial work, definitely more work required to portray a more accurate and comprehensive picture of vulnerability for First Nations, but this provides a good start. And I guess one of the outcomes is with engaging with First Nations, there has been an increase in awareness about this issue, and we've been able to connect with First Nations to get their input on the development and shaping of the flood strategy itself. Next slide, please. And we've done that work through a couple of different processes, meeting with individual communities, hosting workshops with multiple First Nations, and there's work underway to establish a First Nations-led secretariat to continue the engagement and consultation to ensure that the values and interests and aspirations of First Nations are fully integrated with the flood strategy. Next slide, please. So a little bit of some of the results. As you saw on the flood extent maps, there are minor increases in the extent of flooding with climate change, not significant additional area, largely because of solely because of the topography of this area. We've got the low-lying river valley and then very steep slopes rising out of the valley. So not a lot of additional floodplain with climate change, but much deeper depths of flooding and a more higher frequency and magnitude of flooding with climate change projecting out to year 2100. And I guess the other takeaway is that while there's not a lot of additional flooding extent with climate change, there's very extensive flood vulnerability under the current present day design flood. A little bit in terms of lessons learned. We certainly have in mind the need to update floodplain maps and our flood risk analysis as the climate science evolves and as conditions change on the ground. And there may be a need to reconsider the design flood for diking standards, for land use policies, for flood construction levels, as we take a closer look at the influence of climate change on flood hazards going forward. Next slide, please. So some recommendations, and I guess maybe just one other point on that last piece. In terms of considering additional or changes to the design flood, that has to do with the increased frequency. So if the design flood is approximately a 1 in 500 year event, a 0.2% AEP, if that shifts to closer to a 200-year event or a 100-year event, is that historic event sufficient in terms of the standard? So just wanted to clarify that. Next slide, please. In terms of recommendations, they were largely to do with improving the information, filling some of the data gaps, addressing some of the uncertainties. So, for example, the flood vulnerability mapping that was done drew from a variety of topographic data sets that were somewhat variable. So that to get a more accurate topographic layer and some consistency across the region, to represent more specific dike breach scenarios, all of these things would improve the accuracy and improve our understanding of the flood hazards and the kinds of scenarios that might unfold. And basically the recommendations are to undertake some research, to do some more detailed modeling to address some of those gaps and limitations and uncertainties. Next, and I think final slide. And this work is underway right now. So the Pacific Climate Impacts Consortium is undertaking additional analysis on the effects of climate change on Fraser Basin hydrology. And work is underway to develop a two-dimensional hydraulic model for the Lower Fraser. So we can go beyond that simplistic extent of water levels across the landscape and do some more two-dimensional modeling to develop more accurate flood extent and depth estimates to get a better understanding of which dikes might overtop or might fail through other dike breach mechanisms. We also will be looking to evaluate the hydraulic effects of different flood mitigation options, such as raising dikes, realigning dikes, flood-proofing areas within the floodplain, those kinds of things, and see do those effectively reduce the flood risk in some areas? Might they cause higher water levels in other areas? Just need to get a better understanding of that, particularly when we're wanting to apply a regional lens to managing this issue. Dike breach analysis will also be possible with the 2D model. And I guess the other two audiences, while we're focusing on more preventative and proactive approaches to reducing flood risk, we do see this as also informing emergency planning, preparedness, and response activities. And we're in touch with Emergency Management BC to see how this tool and the flood scenarios that are modeled and mapped can be informative leading up to next spring's Fraser River freshet. And lastly, we see the model being helpful to raise awareness, to educate the public, educate decision makers and stakeholders about the flood hazard, as well as community vulnerability and risk. And I guess before I close, I do want to acknowledge Monica, who you heard from previously, and Northwest Hydraulic Consultants that did the vulnerability assessment that was the basis of the case study, helped co-author this case study, and are also working with us developing that 2D hydraulic model as a really critical tool that'll be extremely helpful for a variety of applications going forward, including running additional climate change flood scenarios. And I guess last slide, just so you can have a link for more information if you wanted to learn about the flood strategy or other aspects. So I'll close there, and thank you very much for your time and interest.
Great, thank you so much, Steve. Okay, so our next presentation is the case study for the Waterford River. Newfoundland and Labrador. And the speaker we have is Lindsay Wilcott. So Lindsay Wilcott is a professional engineer with CBCL Limited's Municipal and Water Resources Group in St. John, New Brunswick. She is a board member of the American Water Works Association Atlantic Canadian Chapter and is a member of the Canadian Water and Wastewater Association National Committee on Climate Change. So thanks so much, Lindsay.
Okay, thanks, Monica. And not to be confused, I'm calling or presenting today from St. John, New Brunswick on a project in St. John's, Newfoundland on the Waterford River. So I just thought I'd clarify that before we get going. So I'll take the next slide, Monica. Thank you. So the Waterford River, you can see the Waterford River itself and its major tributaries are outlined in blue. The watershed boundary is about 67 square kilometers, and you can see the outline in red. It intersects the city of St. John's at the bottom of the watershed, as well as Paradise and Mount Pearl. You can see the delineation of the municipalities in a light beige color. The watershed, even though it isn't too large, it is highly urbanized and developed. So we do have 99 hydraulic structures along the river. That includes 55 culverts and 44 bridges, all of which were included in the modeling that I'm going to talk about in a second. So the three municipalities, to give you an idea of the size of the area, they have a total population of just under 160,000. I'll take the next slide, Monica. Thanks. So the deliverables for this project were a set of floodplain maps. Those included inundation boundary or the floodplain mapping for both the 1 in 20 and the 1 in 100 year return period events. We also included velocity distribution mapping and hazard mapping, and then a comparison of the 1 in 20 for current climate and current development conditions against the climate change and future development conditions. And we also did this for the 1 in 100 event. I'll have an example of those maps that I'll follow up with as well later in the slides. Next, Monica. So for our modeling, we had a pretty robust data collection program. It included updated LiDAR for the whole area and aerial photography. We field surveyed 433 cross sections. As you might be getting a feel from the image on the right, which is a rendering, the river isn't deep enough for bathymetric survey, so field surveyed cross sections were required. There is an area that at the very bottom that is deep enough, but it just wasn't feasible to do just that one edge, so we did do field surveyed cross sections. We also surveyed all of the hydraulic structures that I mentioned, that's 99, and we had 1 permanent as well as temporary water level monitoring gauges for calibration. Next, Monica. So we have updated IDF curves that were done in 2014 and are also as well being updated again right now by the province. All of the climate change IDFs were created for all of the stations across the province using the same methodology, and that's using the IDF-CC tool. That's the University of Western Ontario tool. That uses 22 global circulation model projections, and I'll talk a little bit about that on another slide, specifically how we included climate change. For flood flow estimation, we used a single station flood frequency analysis and regional flood frequency analysis for comparison against our hydrologic modeling using HEC-HMS. We used both, we modeled both the 1 in 20 and the 1 in 100 year annual exceedance events for this modeling program. Next slide. So I'm sure that everyone that's listening knows, but I'll just clarify. The hydrologic modeling was a conversion of rainfall to runoff, and then our hydraulic modeling software, which is HEC-RAS, converted flow to water surface elevation using the unique bathymetry and terrain for the river. So we used boundary conditions at the outlet, which were for current conditions, high tide, and for future conditions also included sea level rise and storm surge, and I'll talk about those numbers as well. We completed a sensitivity analysis and then also calibrated the model to Tropical Storm Chantal. And we had a simulated water level compared to our HEC-RAS matched between 20 centimeters for our peak flood flows. Let's grab the next slide. So for integrating climate change into our hydrologic modeling, we had climate change IDF curves, like I talked about, for all durations. They were based off the middle of the road emission scenario, that's RCP 4.5. We used the 22 global circulation model projections in the IDF-CC tool at the furthest time horizon of 2071 to 2100, and that resulted in an average increase in rainfall of about 26% at that specific rain gauge for current conditions as compared to climate change conditions. And that resulted in a climate change condition for flood flows 33 to 41% higher than current. But that also would include climate change conditions and future development on top of that. So for sea level rise, we have a storm surge level of 1 meter above sea level rise of 0.7 meters, all on top of high water, large tide for the harbor at the outlet of the river. These are based on site-specific predictions that the province of Newfoundland and Labrador endorsed, and the report is listed right there. we also, for the future conditions, included full development in the town of Paradise, which does not have a no net increase stormwater runoff policy. The other two municipalities do have those policies, so we did not make any changes for the future climate change scenario for development in those areas. So next slide. So this is an example of a deliverable map for the area. We've got two inset maps set in ArcD, and you can see at the top right corner what section of the river is being shown. I'll grab the next one. So this is an example of an inundation boundary. It actually is comparing current climate 1 in 20 against climate change 1 in 20-year floodplain, except the colors have been chosen for printing, but it's a little bit hard to see depending on your monitor, but orange is the smaller of the two and yellow is the larger of the two. So that gives you an idea of the increase pieces or areas of infrastructure that would be included in the climate change scenario. And it's not that extensive in this area particularly, for example. Next slide, please. This is an example of the velocity distribution mapping. So we have highest velocity in red to lowest in yellow, and we're primarily using these to understand where we might see scouring and erosion in the river. I'll grab the next slide, please, Monica. And then finally, this is a hazard map, and hazard is a function of depth and velocity. It's primarily for emergency response and planning purposes and understanding where the highest risk areas may be during a 1 in 100-year event like this. And of course, highest hazard is shown in red and up to lowest in green. Next slide, please. And then we finally did another comparison of the inundation boundaries that we came up with during this study in 2017 against the historical flood extents that were completed over in the 70s and 80s over various time periods. And I'll just take the next slide, Monica. So here are a few considerations looking back on the project at the end. We decided to consider a multi-jurisdictional policies. So I mentioned that one of the 3 municipalities did not have a no net increase stormwater runoff policy. So we did decide to project full build out in that catchment on top of the climate change scenario. So it's not just simply a climate change scenario, it's a future projection of development. This can be quite difficult, but we followed zoning and planning and future population projections for that. The second point, apply climate change IDFs that are defensible. So our climate change IDFs were all completed at the same time across the entire province using the same methodology. And when they do their next update or currently undertaking their next update, the same thing will happen. Every climate change IDF will be based off the same methodology and will represent the same thing. And we think that's good. We'd like to see the IDF curves updated regularly and if possible, have the floodplains also be updated regularly. We didn't have, unfortunately, 30 years of climate data to develop our IDFs, but we'd like to have more if possible. And point 5, many of the models that we looked at predict increased winter precipitation in Newfoundland, and we did focus on past spring flooding, and we just haven't considered what that might look like to date in Newfoundland in the Waterford area catchment. And then finally, we are looking forward to evolving LiDAR survey techniques and hoping that in the future that those type of surveys will be able to penetrate the water surface, or we'll be able to come up with a more feasible way to collect bathymetric survey on large rivers systems that can be quite costly to completing one of these projects. So some of the applications, we're looking at land use planning and drainage criteria for those 3 municipalities, and hoping that no net increase policies will be added to any municipalities that don't have them. Also looking at our hydraulic structures, our culverts and bridges, and where capital works planning may have to be initiated. Identifying flood hazards for emergency management practices, and we talked also about high hazard areas. Also with the velocity distribution mapping, we're looking at engineering design and bank stabilization, and as well the application of the model we created for real-time flood forecasting system for the Waterford River. Next, please, Monica. So I have a video here. I'll just get you to start it. I hope it's not going to be too choppy. It shows the results of the 1 in 100 year annual exceedance probability floodplain. It doesn't have any sound, so I'll just talk you through it a bit. The rendering is based off of the LiDAR we collected, and unfortunately we're in the bottom of the river right now at the harbor outlet in St. John's, and we did not have a buildings layer, so we couldn't really bring the buildings to life here to show you what's impacted, but you will be able to see them as we get closer to Mount Pearl, how the how infrastructure is impacted by the floodplain. And you'll also see inconsistencies at roadways. We didn't take the time to build up those overpasses and put the structures in. We just wanted to represent this in a way that you could really see what the floodplain resulted in 3 dimensions. So we're in the next municipal boundary now, and you can see some more buildings are impacted in this area by the 1 in 100 year flooding event. I don't know if we'll ever get away from printing floodplain maps, but we hope that as they are developed and updated more quickly, that showing a digitized version of the floodplain will become more acceptable. It is a nice way to see the results. It's easily understood by many. And that's just a final aerial look of the entire city. So just to conclude, I wanted to thank the Water Resources and Management Division of the Newfoundland and Labrador Department of Municipal Affairs and Environment for their support. And then the final page, Monica. And yes, thank you very much for your time, and feel free to send me an email if you have any questions that you don't have the opportunity to share today. Thank you.
Great. Thank you so much, Lindsay. And thank you so much to all the presenters, Carrie, Monica, Steve, and Lindsay as well. So now we're going to move to the question and answer period. So I'm going to get Sarah Fruin from CWRA to ask the questions.
Hey everybody. Yeah, thank you very much. We have a few questions already for everybody, which is great. I guess I'll start at the beginning again. So Carrie, what was the floodplain done only? Was the floodplain done only for the downstream end, or was it the damaged centers as well?
The floodplain on my original slide shows the extent of all the floodplains for, say, our ones that are like along the Fraser and along the center of the city. Most of our other floodplains are ravines, or rivers are in ravines through a lot of the rest of the city, in which case your floodplain does not extend outside. you would have more your flood extents from a pipe system in the other part of the city. So we're just dealing with more of our river systems. So when you see the flood extents here, that's our river systems within Surrey and their natural floodplains. But the little creeks that go up off of that are more or less incised in channels, so you don't see them popping out except for maybe crossing roads here and there.
Perfect. Thank you very much. And the next one's for Monica, actually. Was there any discussion on what would be appropriate timescales for prediction of flooding? And if so, what factors came into play?
Sorry, couldn't quite hear you. You're asking about what mitigation measures would be appropriate?
Was there discussion on what would be appropriate timescales for prediction of flooding?
Oh, time scale. Well, it's very much a function of the infrastructure lifespans. So Surrey is keenly looking at end of century flood extents and impacts when considering infrastructure like roads and railways. Residential areas, farming areas likely have a shorter time span.
Monica, but on that too, we also didn't just look at current in 2100. We took various years in between to figure out when different infrastructure will be impacted.
Absolutely, yes.
Okay. So I think that was it for the first case study there. Steve, you've got a few questions here. I think you might have answered one of them already, but how did you combine the river and the sea level? And is there any statistical analysis?
Well, that's the joint probability approach that we took, looking at continuous records of ocean levels and precipitation records. So by combining all the available information, we essentially considered both types of flooding throughout. And this approach really lends itself to assessing climate change impacts. Say in the city of Surrey, looking at IDF curves was not really an option because you often get these back-to-back storms that influence flood levels. So this continuous simulation approach was really the only workable solution we could come up with.
So thank you very much, Monica. Steve, okay, there was one question. Why did you use the 1 in 500 AEP for the Fraser River case?
Sorry, what did we use for the
why did you use the 1 in 500?
Yeah, largely, well, because the current design profile or design event for the Fraser is close to a 1 in 500 AEP. So we know that is a historic event that has occurred and can and will occur again. So we used that, and we thought there'd be some nice symmetry and consistency if we did something. We sort of replicated that for the Fraser River, projecting out to 2100, and then also for the coastal levels. Although in British Columbia, the coastal design flood event is a 1 in 200 AEP.
Okay, thank you. Sorry, there's a lot of questions coming in now, so I'm trying to sort through them and make sure everybody gets. I guess they're saying, Lindsay, you've got quite a few questions coming in. I think, Steve, you've got a few more down the bottom here. Sorry, I'm just reading through them. So Lindsay, St. John, why was 1 in 20 picked for St. John, and what factors came into that decision?
Yeah, I know the 1 in 20 isn't our standard return period event, but it was the one that was used in the past, in the 70s and 80s when the province did some floodplain mapping for the Waterford River, they chose to use the 1 in 20 and the 1 in 100 at that point, and we wanted to be able to compare how our new methods have changed the floodplain delineation, and that's why we chose to stick with the 1 in 20, even though that's not a standard. So yeah, that's a good question. It doesn't relate to any sort of land use planning return period. It was just simply because it was used in the past and we wanted a comparison.
Okay. Steve, back to you. Are the city's water levels used in the development of permitting mentioned by the first speaker? Oh, sorry, by the first speaker. So not Steve. Sorry, that was back to Monica and Carrie.
So it's Gary. What we've done is we've taken some of the levels, and in Surrey we've made a hazard area development permit based on the floodplains and based on where we have steep slopes also, because we have cliff areas around some of our areas. And so then we have that in our land use planning. So developments, if they fall within any of those zones, have to design differently. So we've been trying to integrate some of these findings into future land use planning.
Thank you. One more for Siri. Did the climate projections for future rainfall consider potential changes in the type of storms that are bringing rainfall? Or is the change field method applied?
No, it's also looking at, so we've done it a few different ways because we've already updated our own IDFs a couple times now, and even our local ones when we updated them a few years ago, some of our storms are 30% different. And also, we don't just have one, say, IDF or rainfall distribution for the whole city. We actually get more rain in the northern part of the city than we do in the southern. So just an example of this week, we had, in 2 days, we had 140 millimeters in the north part of Surrey. We had 50 millimeters in the south part of Surrey. So we don't have the same distribution across, but the predictions are showing that our distribution difference is getting smaller, and that the storms are getting more intense when you start looking at them. So when we were looking at, when Monica was doing, say, for this bigger flood study, they did look at the distribution and we're taking out the longer events and making them shorter, more intense events in the continuous simulation.
Thank you very much. One more question for Steve, and then I have a couple more for Lindsay as well. For the Lower Fraser study, how was the 17% increase for the 1 in 500 year event climate change determined? Oh, I don't know. Steve, did you?
Oh, sorry, I had my phone muted as well. Sorry, I am here. Double muted. Sorry, can you repeat the question?
Yeah, for sure. How was the Lower Fraser for the how was the 17% increase for the 1 in 500 year event under climate change determined?
Yeah, so that was it was a moderate climate change scenario that was selected, and this was pulled from the Pacific Climate Impacts Consortium did some hydrologic analysis, and I think Northwest Hydraulic Consultants was part of that as well, and they generated peak flows for about 140 different flood scenarios, and that 17% was what sort of the resulting peak flow under that moderate climate change scenario for the 1 in 500 AEP.
Okay, awesome.
And I guess I should say that the higher flow is anticipated to result from a faster rate of snowmelt in the year 2100 and a higher probability of heavy rainfall coinciding with the freshet. Although we will expect a smaller snowpack in the future, those other two factors combine to generate higher peak flows.
And I might just add that we looked at 8 global climate models, and then the different scenarios of A2, A1B, and B1. And we picked first a really extreme event, found that was way too much, and reduced it, and then also investigated a more moderate scenario, and the moderate scenario actually corresponds to this 17%.
Thanks, Monica.
Okay. And Lindsay, has the known limitations of IDF statistics been taken into account?
Could you just repeat that for me? Sorry. Is
Sorry. The known limitations of IDF statistics.
Has it been considered in?
Yeah, that's all that the question was.
So it's Monica from Natural Resources. I'm wondering if they're talking specifically about the Lindsay, I believe you used the tool from Western University.
Yes.
And I believe there is some there are some limitations to that tool. So I wonder if that's what that question is referring to.
There is definitely some limitations to the tool, but I think I can't remember exactly what the question was, but yeah, in terms of using that tool, it's definitely not it's not the best tool for every application, that's for sure. It has its strengths, so it's a very easy to use and straightforward application. Of course, ensemble modeling isn't going to always give the most conservative output, or maybe it's going to give a very conservative output depending on the application. So it is in the province of Newfoundland currently the tool that's being used to increase IDF curves for and account for climate change. If it wasn't a policy, we would have for this project looked at many different prediction methods and decided which one was the most applicable for the situation. But since it was in the province today, the preferred method, that's the one that was used for this project.
Okay, I think that answers quite a few of the other questions that are still on the list here. So a question for everybody, actually. Is anyone aware of how well the climate models are resolving phenomenon like changing convective dynamics? And quiescent, I don't even know what that is, because quiescent amplification and how well this is incorporated in the updated IDF curves, if at all. Quasi-resonant, sorry. It feels like a Monday. I don't know if anybody wants to try and tackle that question. I can repeat it.
In the Lower Mainland study, we didn't look at IDF curves. So yeah, I personally don't have any knowledge about that.
Okay.
In Surrey, we don't use IDF curves for our floodplain area. We use them more for designing our pipe systems on the uplands, which are more governed by the short duration storms. When I'm looking at long duration storms and floodplains, they don't help me at all. You've got to look at more, like Monica was saying, the continuous simulation. You can't just run these short events. The patterns are too long. We'll get flooding. We'll have rainstorms back to back for weeks, which we're currently in right now. So there are two different scenarios to examine flooding, whereas IDFs are typically for your shorter storms, not your long ones.
Yeah, just to add to that when you're using a continuous simulation approach, IDF curves are not applicable.
Okay. That's pretty much it, unless anybody else has more questions that they'd like to sneak in. There was one comment, Lindsay, somebody was asking what software you used to make your video.
Oh yeah, that's Civil 3D.
Okay.
One thing I'll add from the earlier question on the different types of tools for climate change projections on IDF, I think that one way there's a lot of uncertainty about climate change and how that impacts rainfall and projecting future rainfall. And I think one way that has worked well in the past is to actually translate that uncertainty in the rainfall to a resulting floodplain. And then once those different projections are plotted, you can decide based on the spatially, what's the additional infrastructure that's impacted and how do you want to deal with that? So translating the uncertainty into a resulting floodplain can help you make a decision on how you want to deal with it. So is there a cost benefit to planning around some of the more conservative results, or would we rather lower? And I think some people were wondering, we used RCP 4.5 instead of 8.5, and running both of them ideally and then plotting the floodplain would be the best option to understanding how those pathways are going to affect the use of these floodplains and the results and the application of the floodplain delineations.
Hi, this is Monica from Natural Resources Canada. I just want to say that Lindsay, yeah, thank you. That is a really great point. And in climate change adaptation in general, when you're planning based on climate projections that do have a lot of uncertainty, like Lindsay said, that we find that once you sort of look at the risk thresholds that you're dealing with, that uncertainty, the sort of range that you're dealing with, it's easier to sort of identify which end of the range you want to be in. So, for example, if you're looking at critical infrastructure like hospitals, things like that, you want to use sort of the more conservative estimate, things like that. So, yeah, thank you, Lindsay. That's a great point.
Awesome. And just one last question that came in here. I think it's more of a statement, but have you completed flood risk mapping considering both hazard and consequence? This person thinks that the words risk and hazard have been mixed up in different case studies.
Yeah, it's Steve here. The vulnerability assessment looked at consequences. So we looked at damages to buildings, agriculture, infrastructure, and some indirect losses related to delays in cargo shipping. So that was sort of a first take on the consequences. And we definitely, with this new 2D hydraulic model, we really envision using that for additional, more detailed, more comprehensive risk assessment in the future under a variety of different flood scenarios.
Thank you, Steve. And that's pretty much it for all the questions. Monica, I don't know if you want to wrap up.
Yeah, so again, I just wanted to thank our speakers again, and thank you all our listeners for joining in. Again, the webinar will be recorded and sent out, and the presentation slides will also be available. We'll also send a link to the case studies documents that these presentations are based on, and we'll also send a video or a link to the video from the City of Surrey where the sound didn't work. So thank you very much.
Thank you, everybody, for joining in today, and have a great weekend.
Thank you. Bye now.
Thank you. Bye.
Thanks. Bye-bye.